Good morning, everybody. Yeah. So it's a busy title, but essentially what we are doing here is there are two contributions. One is we are essentially looking at ensembling of a bunch of features which are the CNN pooling features and some more traditional color texture features. And the other is you're integrating the classification scores across different magnifications. So this is essentially targeted for a breast cancer classification task, which is basically right now we are doing a binary classification. It's benign versus potentially malignant cases. Important for primarily triaging, which has a lot of focus in developing countries to reduce the patient load and so on, or to optimize the patient load. Right. So that's the basic motivation of the project. Right? So this is the idea, that we are ensembling classifiers which are trained with different features. I'll get a bit into the bit more details into the features. And what we are essentially saying here is that even if we have a bunch of features, not all of them would be useful. So feature selection is actually an important task, and we actually show some interesting results for that. And the final sort of a secondary contribution is that if we have images from multiple magnifications, if we do sort of a weighted combination of the final classification scores from each of these magnifications, then we arguably get better results as for the final accuracy. Right. So each of the basic unit that you see in this diagram, the basic unit here, is essentially made up of CNN pooling features and some color texture features. And then we feed it into a support vector machine classifying, and then whichever features are selected using the information theoretic measure are then fused using a product rule. So these are the features, these are the color texture features. The thing about color texture features as opposed to normal traditional texture features is that, these features in some sense exploit some sort of, correlations between the different color channels while defining the texture features. So, because of, time constraints, I'll not go into the details, but, you're welcome to discuss with me, at the end. Right. And then we select also a bunch of CNN features, which are the features from the pooling layers. These are 5 pooling layers from a 160 layer dense net. So we don't choose features from all layers. We only choose features from the pooling layers. Right. And this is a way to select features. So we have about 8 features from the color texture channels, and we have 5 pooling features. And then the idea is that because we know that not all features could be equally important. This is essentially a work in 2010. We're borrowing the method from that work, and the idea is that we are iteratively in a greedy fashion, adding the features which sort of maximizes the mutual information between the the class labels which are sort of best up to the previous iteration, and the next set of features which is essentially chosen is to maximize the mutual information between the classification accuracy of the currently chosen features and the classification accuracy till now. Of course, this classification accuracy is evaluated on a validation data, and then we have a separate test data for evaluation which evaluates the performance on the selected features. Right. So very quickly we use the Breakis dataset. Now this dataset does not have whole slide images. Actually, these are sections from whole slide images, which consists about about 8,000 images across 58 patients, and these have 4 magnifications. And our sort of training, validation, and testing fraction is 40%, 30%, and 30%. Right. So just to highlight one point, here we find that say some features, for example, these features perform the best, right, among the various bunch of features that we choose. And the point is that we see that if you look at the scores, you'll see that at different magnifications there are different features which are performing, with different accuracy. So the idea is that there's no one consistent feature which performs equally across all magnifications. Now this is the important part. So if you look at the the accuracy when we choose all the features, that's here. And if you look at the accuracy when we choose selected features, and the one which are marked with asterisks, these are the selected features, we can actually see that we get a significant jump if we get rid of a few features. That means some features are actually affecting negatively, and we need to do some sort of a feature selection to get rid of these features. And these are the accuracies which were highlighted in the earlier slide. So clearly the accuracies with the performance with selected features are better than performance with single features, as well as the performance with when using all the features. And about the secondary contribution, and our model which is sort of integrated over all magnifications. So basically it integrates scores, performance scores from all magnifications, performs somewhat better than all cases. It's sort of closer to the 40x, just using 40x magnification, but then it is a little more reliable in terms of the variance. Yeah. So that's the thing. Yeah. This is some comparison with some state of the art. So except for this particular work, we are generally doing better than the rest. But of course, sort of all of the methods use different networks, and the comparison. So the primary goal of our study is you give if you have an existing network, can you do an ensembling using features from individual layers of the network? So we could do the same thing on a network with this configuration and so on, right? Yeah. So the takeaway is that because we are actually dealing with features at different layers of the networks and also some traditional features, we shouldn't just rely on the features from the last CNN layers, which is typically done in a standard CNN approach. You take the features from the last CNN layers and feed it into the classifier. We've actually seen this across different studies on cytology as well. So we've done some work on pap smear cytology and HEP2 cell classification and so on, and we've actually come up with similar conclusions and so on. Obviously feature selection works, so even if your CNN is performing great, always feel free to explore which layers of the CNNs are perhaps contributing more towards the actual classification. And an interesting finding is that traditional features do actually provide complementary information. We still have to exactly quantify what complementary information is this, but at least in terms of performance, they help, right? And finally, a model which is integrated over all magnifications seems to perform better than than the one which is sort of trained over individual magnification images. Yeah. So thank you. I'll welcome questions.
Any question from the house? Yeah. So did you think? Did you find any problems with color normalization and the variation in the color stains? Did it affect your performance across the cases?
Right. So because this is a standardized data set, we did not the data set is sort of reasonably normalized with respect to the color scheme. So I mean now that we will work on more realistic data set coming from hospitals and so on, we will have to check that. Yeah.
All right. There's one question, last question we can take.
Yeah.
Thank you. Hi, great work.
Thank you.
Max Reshi from Philips Research. I was wondering, it's maybe a comment or a question as you take it. When you talk to pathologists, they would say, I would go from 40x to 100x, or maybe 10x to 100x.
Yeah.
Whereas you have gone on to 200x
Yes.
and so on, which is very interesting. Right. So have you ever thought of like mimicking how a pathologist would
Yeah,
do?
in fact, we're doing that, in the cervical cancer pap smear study. So, unfortunately, because this is a public data set, the strategy which I'll mention now is not really, applicable here, because we already have the images and we don't have the registration between what region of the 40x corresponds to what region of the 400x, right? So ideally, you know, a study across magnification should be more sequential, that, you know, at 10x, you know, you make a decision, and you know, to get, you know, better confidence, then you basically select region from those, you know, 10x images, and then study only those regions from 40x. So in terms of, you know, a processing pipeline, also workflow, this makes the system more efficient, because each whole slide image can have actually a few thousands of these regions. So we are actually doing, you know, planning to do something like that with our industry partner for a cervical cancer, you know, cytology study. Yeah.